Mario and I are very much looking forward to presenting some information for you about the field of model building and predicting properties in drug discovery. I'm going to start with thinking about what models we should predict, and also when won't predictive models be appropriate. Mario is then going to talk to us about how to go about building your own models and some of the considerations in that area. And then we'll go into a short demonstration of StarDrop's auto modeler, which enables anyone using StarDrop to build and validate their own models for properties tailored to your projects and your chemistry. And then at the end, Mario will come and I will come back together, and we'll be very happy to answer any questions that you have. So let's start about thinking, well, what should we predict? And when we're working in drug discovery, we're not only thinking about the potency of compounds, but there are many different properties: solubility, metabolic stability, absorption, safety, just to name a few. These are all things that we need to consider in our projects if we're going to get from that initial hit or lead compound that shows some degree of potency to this sweet spot here where we've got this optimal balance of all of the important properties for our projects. It's also important for us to know when we're not going to get that balance and no good drug is going to be available. So being able to predict these properties and use that as part of a multi-parameter optimization strategy in your project can be particularly important. It can also help you to avoid any surprises later in a project where you might have optimized your compound and then find some late stage toxicity or other liability that you weren't expecting. So property predictions really form a very critical key part of a medicinal chemist or a drug discovery scientist's toolkit for their project analysis. So which properties should I predict, right? And there's a whole range of them. I've got a few here. You know, we could think about some of the physicochemical properties. These are things like solubility, the log P or log D, pKa's. These are important properties because they often are good indicators for other properties such as absorption or for activity at other enzymes. They can be surrogates for that. For example, if we're thinking about metabolism, the CYP3A4 enzyme, log P, log D is a very good surrogate for whether a compound is likely to be metabolized. There is often also plenty of measured data for these properties from which you can build a model. We can think about some of the other ADME properties: absorption, distribution, metabolism, excretion, toxicity as well. And I've got a few listed here that are models that Optibrium provides as part of our ADME QSAR module. And these are all things that are important to consider during your project. You know, is my compound likely to be absorbed? If I'm looking for an orally bioavailable compound, this can be particularly important. Is it going to penetrate the blood-brain barrier? You know, we want that to happen for a CNS compound. And are there any surprises or off targets that we need to consider? Things like cardiotoxicity. So having a range of these models is also very useful, as I said on the previous slide, for keeping track of these, even early in a project. helping to assess the potential of an early lead compound. What are the potential pitfalls that might come my way? We can also think about being able to predict metabolism properties. So using the QSAR approaches that we're talking about today, it's possible to build models that will predict whether a compound is a substrate or an inhibitor for one of the metabolism enzymes. But we also have a different set of predictive models that think about regioselectivity, metabolic stability, and metabolites. Those are part of Optibrium's metabolism module. And so that can answer some of those metabolism questions in more depth. And then we could think about models for predicting SAR. You know, what's my potency for the receptor that I'm interested in for my project? Is there an off-target effect that I'm keen to understand the selectivity? So the ADME QSAR module that we're going to see a demo of today is ideal for being able to build models for your project and your chemistry and your series to think about some of these potency questions. Now, we also often get asked about 3D approaches for predicting SAR. And QSAR models are typically 2D approaches, but there are some 3D methods out there. One of them would be the Quanza approach in the Biopharmics platform, which is building 3D models to be able to think about the binding affinity of compounds. So when we're thinking about which properties we should predict, it's important to consider the purpose of the model. Are we looking for a model that will predict the absolute value of this compound? Or are we looking for a model that is really going to help us prioritize our ideas? Should we synthesize this compound? Or should we progress this compound to an experimental assay? And so you can think about continuous models versus categorical models that bin the compounds. Depending on the amount of data that you have and the quality of data, you might choose to build one or other of those types of models. Now, that also brings me to the next section, which is, of course, well, when won't these models work? And when shouldn't we be thinking about building predictive models? And the first point here is, well, do we have sufficient data? And is that data of sufficient quality? We also have to be sure that we have an appropriate split between the training set and the test set. For example, you need a balance of both active and inactive compounds in both the training and test sets to build and validate your model appropriately. If you don't have that split of both active and inactive compounds, you might build a model that just isn't able to differentiate an active compound from an inactive one, and that's going to bring very little value to your project. It's also important to make sure that your test set is representative of the training set so that you can appropriately carry out that validation and have the confidence that you'll be able to go forwards and apply that model prospectively. This can occur if you're clustering your compounds and all of the training set compounds come from one cluster and all of the test set compounds came from another cluster. And so those test set compounds just wouldn't be within the domain of applicability of that model. Another thing to consider is the variability or confidence in the measured data from which you will be building your model. If that's very noisy, then it's going to be much more difficult for any model that you build to make confident predictions that you can use in your research. Iteration is the descriptors that we use. For some of these later stage in vivo ADME properties, things like clearance, these can be really hard to predict. A lot of model building approaches struggle with making predictive models for properties like this. And this is because they're very complex properties that involve a lot of biological processes. And so it's important to have the descriptors that reflect those biological processes. In our AutoModeler module, we have a set of descriptors, both whole molecule descriptors and SMARTS fingerprints. But for a property like this, there might be other descriptors that you would want to bring in as part of your model building process. Now, we can think also about, well, is it even valuable to build a model for this property? And one example would be where you've got very promiscuous enzymes and many compounds show activity at that enzyme. Is the model ever going to really be able to differentiate between those that do and those that don't? Is there sufficient data? Or in your project, is it going to say that everything is active at this enzyme? That's going to bring you very little value. This might be an example of where we could use one of those physicochemical properties to be a surrogate for activity at one of these enzymes. And then the final point I wanted to talk about was the domain of applicability. So when we're building a QSAR model, the model knows all about the compounds on which it was trained and can make predictions for similar compounds. But they struggle to extrapolate into new areas of chemistry space. So as you expand and explore new chemistry, you might find that a model is less able to make predictions with confidence for that new area of chemistry. So thinking about the compounds from which the model was built and whether they are representative of the compounds that you want to be able to predict. As you extrapolate into new areas of chemistry, the models that we build all come with a confidence in the predictions that we make. And as you see that confidence dropping down, that would be an indication that this model is no longer applicable for this chemistry. And perhaps then it's time to rebuild a model. We can also think about local versus global models. Global models are those that are built on a wide range of different chemistry and are applicable then to many different projects. The models that we provide in StarDrop, these are all global models. However, local models built for a single project or series, they have the advantage that they're better able to tease apart the small differences in SAR within a series of compounds. On the flip side, they can't extrapolate into new areas of chemistry, and so more quickly you would find that that model would need to be rebuilt. So these are some of the considerations to say, well, should I be building a model here, or is it appropriate to use my model for this particular function? So what I'm going to do now is hand over to Mario, and I'm going to let Mario take control of my screen, and he's going to talk to us all about how to build models.
Thank you, Tamsin, and hello to everyone. So I've been working at Optibrim for about 8 years, and we decided that it would be nice to kind of share my experience about building models. And I like to think about models or building models in the sense that we have 4 pillars. We have the data, and we need to curate that data. Then we need to choose a method. How do we want to model that specific property we're interested in? Then we need to validate the model and obviously measure the performance to kind of get an idea how good that is. Let's start with data curation. The first question people often ask me, but I also ask the question from myself when I start a new project, is how much data do I actually need? And unfortunately, it's not a clear-cut answer here. And I would like to show you this little graph I made, and it partly covers what Tamsin has already said. But on this graph, we have just one axis, it's the x-axis. And on the right here, we have more data, and on the left, we have less data or fewer data points. And as Tamsin said, the more data we have, the likelier it is that we can build a global model, which essentially has a huge domain of applicability and most likely can give you a reasonable prediction for any molecule you can think of within reason, of course. But if you don't have as much data, then you can build local models and as Tamsin said, they can still be very useful for certain chemistries. But when you start to diverge from these chemistries, then the model is not going to be as useful as a global model. And as Tamsin said, you probably need to rebuild the model with additional data. The other thing which I would say is that if you do have more data, then it's more likely that you can use data-based approaches. And I'm talking about models which are based on, say, smarts patterns or fingerprints or any other descriptor which is really quickly you can calculate it really quickly. And the pro of this approach is that once the model is built, the model is very fast, and if you want to get a new prediction for any other compound, then you'll probably get it within a second. Now, if you have less data, then it doesn't mean that you can't build a model. You can still build a model, but it's more likely that you need additional descriptors which are physics-based. So maybe a value from a computational chemistry calculation, or maybe a value from a docking study. And in these cases, your model is going to rely on these longer calculations. And while it might still give you good results, it's going to be slower compared to the data-based approaches. Then, as Tamsin already said as well, it also depends on the property you want to model. So if it's going to be an in vivo property, then I am generally not sure if we can model it or not, because as Tamsin said, these processes are very complicated and depend on many different factors. With in vitro, it's easier because we often control various properties. They're fixed for our experiments. So there are less variability in the data. And building a good model also depends on the quality of the data. And here I would like to add another axis on my little graph. So on the y-axis, we have variability or noise. And in the bottom of the graph, you have more noise, and in the upper part of the graph, you have less noise. And I would very much go over my data set and make sure that I don't have a lot of variability in it. There have been studies, and we have noticed it ourselves as well, that smaller but cleaner data sets will give you better results. And it's natural to see variability in experimental results. especially if maybe the data is not from your own lab. If you use public sources, then there are different labs, they have different experimental protocols and so on and so forth. But clean data is important. And one of the things which I always do is I remove compounds that are ambiguous. So if there are two studies which give you completely different results, then it's better not to have those compounds and have less data than have those compounds but have noisy data, which probably kind of makes the signal worse in the end. Now, one question is, can I train a model with noisy data? And yet again, it depends, but generally the answer is yes. And I'm going to talk about it in a second, but this question is actually a nice segue to our second pillar, which is the method selection. And before I answer the question, the first question you should ask yourself when starting to build a model is, should I train a regression or continuous model or a classification model? And it does really depend on the data. And now we'll go back to the question I asked in the previous slide. What if I have a noisy data set? And you can see here there's a graph with a bimodal distribution. And say, for example, this is a property you want to predict or model. However, there's a lot of noise in the data. But you can see that although there is a lot of noise in the data splits nicely into two regions. And let's say that on the x-axis we have activity, and say here we have the active compounds, and here we have the inactive compounds. So due to the noisy data, you cannot build the regression model because it's not going to be accurate enough for your purposes. But what you can definitely do is take that data and build a classification model. And in this case, say, for example, you are interested in active compounds. You cannot predict how active your compound is going to be, but you can filter out the compounds which are definitely not going to be active. So to answer the question, even with a data set which is very noisy, you can still squeeze out useful information for your project. We already talked about descriptors, but essentially what we usually do is we use smart space descriptors. We also use descriptors from other models. Tamsin mentioned pKa and log S. So you can have these model results in your model as additional descriptors. And we can also have descriptors from various calculations. In our metabolism module, we actually use semi-empirical methods to predict the site lability, which means that compared to the regular QSAR models, the metabolism models are slightly slower, but they do have a great domain of applicability due to the fact that we use computational chemistry, semi-empirical methods. And now once you have the data, you're certain that, this is the way I want to go. You know the descriptors, what you're going to use. Then the question is, which approach should I choose? The most common approaches one could choose are maybe decision trees or random forest, but then you could choose something more complicated as well, such as Gaussian processes. But the thing is that it is hard to know which method to use a priori because there isn't a clear cut with which data set is suitable with which model. So then we go to our third pillar, which is model validation. And we at Optibrium, what we like to do to answer this question, which modeling methodology should we use, is we take our data set and we divided it into three. So 70% goes to training the model, 15% goes to validation or validating the model, and then the last 15% we take away and we just don't do anything with it during the training process. And sometimes we even use an external test set, but it's not necessary when you have a large enough data set. And obviously, when splitting the data, what you have to do is what Tamsin just spoke about. You have to make sure that the training data is representative of the validation and test data. So we train the 70, we use the 70% of the data for training. And what we do is we use different methods. We use different sets of descriptors, and we validate that on the second 15% of the data. And from there, we kind of choose the model which behaves the best, which gives us good statistics, and which seems that it's doing a good job. And then, and only then, we're going to use the last 15% to test our model. And this happens only once. And if the test set results are horrible for some reason, then we'll realize that the data set we're using is not probably suitable for a model, or the descriptors we have chosen are not describing the effects or factors which go into the experimental results. And essentially, we probably either have to move away from those descriptors or use an improved data set. Now, it is important to understand that you can't always divide the data into 3 sets, and from time to time you don't have a large enough data set to have those 3 sets, but there's still enough data to build a model. So in these cases, what we do is we use the 80-20 data split. 80% is for training, 20% is for testing. And yet again, we test this model on the test set only once, just to understand if the model works or not. And obviously now we don't know which method to choose or which descriptor set is the best for this specific problem. But in this case, we usually turn to the literature, and you can definitely find hints in the literature what methods have proven to be useful for a similar problem. And yet again, if the test set still proves that the model is not working really well, then it just means that this specific property probably is not modelable at the moment. So maybe we need more data, maybe we need better descriptors. And last but not least, in cases where the data set is truly very small, we do an n-fold cross-validation. Usually what we do is 5-fold cross-validation, but we'll have also done 10-fold cross-validation. And what it means is that we take the data set, we divide the data set, say for 5-fold cross-validation, we divide it into 5 sets. And the first set is for testing, and the rest of the compounds are for training. We train the model, we test it, and then we take the second set, use this for testing, and everything else for training, and and so on and so forth. And we get into altogether 5 models. And to predict new compounds or the results for new compounds, we do consensus modeling, where we take the results for all 5 models and take the average of those results. So just to reiterate, in the perfect case, we do the split 70, 15, and 15. And the middle 15, or the validation set, helps us to pick a strategy. It helps us to pick a modeling method. It helps us to pick the descriptors. And sometimes it also helps us to understand that, hey, maybe we need to oversample our data. And this is something which Tamsin talked about before, that sometimes the data is really unbalanced. So say, for example, you have a lot of inactive compounds and not a lot of active compounds. And this is the situation you see here on the right on the slide. And in these cases, what we usually do, and this is something we do only for the training set, we essentially copy the active compounds, in this case, these columns here, and paste them into our training set, just to balance out the active and inactive compounds. And what it does is it gives more weight to the properties or features of these compounds, and then the model learns from these features. And You always don't need to do that. There are some modeling methods which automatically take that into account and give more weight to undersampled data points, but you can't always choose those methods. So oversampling is still a valid strategy to use. And I said it 3 times, but I'll say it again. The test set should only be used once you have optimized all of your methods and descriptors you're going to use. And as I said, if the test set doesn't provide you with good results, then maybe it's not time to try to model this property yet. So maybe you need more data, or maybe you must use different descriptors, because these descriptors, what you're currently using, are not describing your compounds well. Now, the last question, or the last pillar, is measuring performance. So how to determine if your model is actually good or not. And for regression models, or the continuous models, most people use R-squared, which is a valid strategy, and you should use that. But you should also inspect the results visually. And there are 2 sets of data which I recommend for you to Google. It's the Anscombe's quartet and the data source dozen. And the Anscombe's quartet is here, and you can see that we have 4 graphs of points. And the idea here is that for all of those graphs, the R-squared measure is the same. And say, for example, if you have a model where the results are something like this graph over here in the top left corner, then that's fine. But if you think about the model or model results, I should say, in the lower right corner, then if you just look at the R-squared, then the model probably is reasonable, and you might expect that, okay, this model gives me good results, so I'm going to use it. But if you look at the graph of the R-squared, then you can see that this R-squared is artificially made better by this little point here on the top right, and all of the other predictions essentially are useless. So this is something you should definitely always look out for. And then you can use other commonly used statistics such as RMSE or MAE. These also give you an idea how well does your model perform, and how big are the error bars on your model. Now, this is for regression models. For classification models, people tend to use accuracy as the performance measure. And it is important to know that accuracy only works when your test set is balanced. If it's not, then accuracy can be very misleading. And I'm going to give you a very silly example, but I think it illustrates the problem with accuracy quite well. So say, for example, you have a friend who has trained a classification model, a model which differentiates between cats and dogs. So if you feed the model an image of a cat or a dog, it will identify if there's a cat on your image or a dog on your image. Unfortunately, your friend has done a horrible mistake in the process of building this model, and the model is completely useless because it only predicts cats. So it doesn't matter which image you give to the model comes back with a result. Yep, this is a cat. Now, you don't know that. Your friend doesn't know that either. And your friend asks you to test this model. And for some odd reason, you have 100 images, and 90 images of these are cats, and 10 images are dogs. And if you run those images through your friend's model, then it turns out that you get a model which is 90% accurate. So 90% of the pictures were correctly identified, and 10% were not correctly identified. You go back to your friend, say it's all good, your model is really accurate, but in actual reality, it is a useless model. So what I recommend you to do is use balanced accuracy, which takes that into account when your test set is biased towards one class or the other. Or what we at Optibrium do is we also use Cohen's kappa. Now, unfortunately, I don't have time to explain how the Cohen's kappa works, but I can say that it does take the bias in the test set into account. and we're going to have a blog post about it at some point. So yeah, thank you. That's all from me, and back to you, Tamsin.
Thanks very much, Mario. And so in this next section of today's webinar, we're going to go through a short demo of StarDrop's auto modeler, which will show how in StarDrop you can very easily build and validate your own models. What I'm going to do is just run through the process that Auto Modeler uses. So this is very much as Mario was talking about, where we start with a data set, and the first step is to split that into the training, validation, and test sets. For each test and for all of the compounds in each of these groups, Auto Modeler calculates descriptors, and we have a range of 2D smarts descriptors, log P, polar surface area, molecular weight, charge. These have been shown to be incredibly robust in the modeling that we have carried out. And then the auto modeler, you'll see, will apply multiple different modeling techniques for building the models. We have both techniques for continuous models or regression models, which are shown here, as well as a lot of decision tree approaches for the categorical models. We use the validation set to evaluate the models that have been produced and determine which is the best model. This is then tested with that independent test set that, as Mario said, should be only used once right at the end of the process. And that's to ensure that the model is going to continue to be able to be used prospectively. And then we'll see that you can submit new compounds to get the predictions. We get not only the predicted values, but also the uncertainty in that value. And StarDrop produces what we call a glowing molecule. And the color here can help you to understand which parts of the structure are having a big impact on raising or lowering that property. And if you want to learn more, then there is a paper. It's available on our website as a preprint. And, you know, I would suggest going in and taking a look at that in more detail. So what I'm going to do now is I'm going to go over to StarDrop and let me see if I've got StarDrop open here. I do. Brilliant. Okay. So here in StarDrop, I have a data set preloaded of 129 compounds that have a measured Ki against the muscarinic acetylcholine receptor M5. And as you can see, these molecules contain a variety of different structural motifs. These are compounds that have been taken from Chembl, where their activity was published. On the left, I have a histogram that shows the distribution of the Ki. And in this case, this distribution is not appropriate for model building. And that's because the very active compounds fall within this bucket with the low values for Ki. And that's where the majority of the compounds, 98 out of the 129, reside. So if we were to build a model, it would be able to differentiate out the inactive compounds, but it wouldn't be able to differentiate potent or active compounds. So what we can do, though, is we can convert the Ki over into the pKi using the function editor in StarDrop. And I've got that function saved just for speed, and we can create this new column, which is the pKi. If I were to plot a histogram of the pKi, what we see is a much more balanced distribution of values. And now the active compounds are the ones with the high values. So any model that we built should be able to differentiate out those active compounds from inactive. So let's go and run the auto modeler. And that's done very easily on this auto modeler tab. And all we have to do is click on the blue arrow at the bottom to start the wizard that guides us through setting up the model building process. We can choose whether we want to build a continuous or regression model or a categorical or classification model. And then we can let AutoModeler do that split of the training, validation, and test sets for us. Give the model a name and choose the property that you want to build the model for. And at this point, we could just click Finish, and it would go off and do all of the model building for us. But let's take a look at some of the steps in the process. So here's that training, validation, test set split. Mario talked about the fact that we usually try to use 70, 15, 15 there. We also have some different ways of carrying out the splitting. In this clustering technique that we're going to use today, we cluster all of the compounds. We take the cluster heads and the singletons into the training set so that the model will cover the most chemical space possible. Then we fill up the training set with additional compounds from the clusters and also use cluster compounds for the validation and test sets. Let's click Next. And here we can choose the descriptors that we want to use. So as I mentioned, the auto modeler comes with a variety of whole molecule and smart spaced descriptors. You can also import your own descriptors and make those available to auto modeler. And that can be useful when there are external descriptors that you might want to use. They can also be in additional data columns, but if you do that, then they would need to be available for anyone who is also going to predict from the model. Now, we've got a lot of descriptors. We're going to let AutoModeler select the ones that are most relevant. And we're going to exclude any descriptors that just don't occur in many of the molecules. They're not going to bring much valuable information to the model. We're also going to think about, are there highly correlated descriptors? If we include both of those, that risks overweighting related properties. And so in this case, we're going to say if they're very highly correlated, keep one and exclude the others. Now, here are the different model building approaches. We have 10 available here for the regression models. And as I said, we have other methods available if we were building a categorical model. These are grouped according to the amount of compute time they're going to use. So for this demo, I'm going to exclude the more intensive methods and just click Finish. And what happens is we get some progress on the left of the screen. You can see it's starting the session. It's now generating the models. And there's also information that we can get here, such as looking at the details for the session. This would tell us which descriptors were used, which compounds go into the training set, the validation set, and the test set. Now, when all of the models are complete, you can see the statistics overall. and we can look at the statistics for the training and validation set. And this is telling me that the random forest model has been assessed as being the best model for this particular set of 5 models that we've produced. We can go and take a look at that model, and we can see here the training compounds, the validation compounds, and the test set compounds. And so this is what Mario was talking about, where you want to look at that distribution when you're considering the R-squared. But if this is a model that we want to keep, then we can go ahead and save that model. You can give this a name. So this might be my M5PKI random forest model. It's M5PKI built in the webinar. And maybe we say here it's built from KI converted to PKI. So this is important information that can be useful if you're sharing these models with your colleagues so that they can understand what this model is built from and therefore where it's appropriate to use it for predicting. So I'm going to go ahead and just save that model. And if I go to the models area in StarDrop, it might be here. There it is. And here you can see those descriptions that I added in, that little bit of extra information. But we can now take this model and use it to predict the properties of some new compounds. Now I have a second data set here of 10 new compounds. So I'll select this model and go ahead and make that prediction. And so here we now have those predicted values for the 10 different compounds. We can also look at this in terms of the, let me see, this one in row 6 looks nice. In terms of the glowing molecule, here in red are highlighted parts of the molecule that are having a positive impact on this model and raising that predicted PKI value. Here we have some blue areas that are lowering it. You know, what would happen, for example, if I take out that nitrogen of the pyridine and convert it to a benzene? That's resulted in an improvement in the PKI and reducing the amount of the blue coloring in the glowing molecule. So I can add that molecule over into StarDrop. We also, just to show you, we also provide a confidence in all of the predictions. The fact that these are all the same tells me that these molecules are all falling within that domain of applicability for the model. And if I started to see a higher uncertainty here, then that would indicate to me, oh, it's time to rebuild my model. So a very quick look through there at how you can use StarDrop's auto modeler to build and validate your models. And before we go into the Q&A, I think we have a couple of conclusions here. So some of the things that we've talked about in today's webinar are that it's really useful to be able to use these models in drug discovery. There are many models that are amenable to model building, things like potency and some of the ADME models. It can be more challenging for some of those complex late stage properties. Successful model building depends on a number of factors, as Mario described. things like having appropriate, clean training data that spans a range of activities, using the model building techniques correctly, thinking about the type of model that you want to build, categorical or continuous, and making the right training and test set selections. And then I gave a demo of our auto modeler, which allows anyone to confidently build and interpret the predictive models. It's not necessary for you to be a computational expert. And so with that, let's move over into the questions section.
Thank you, Tamsin. Thank you, Mario. As a reminder, if you do have any questions, please add these to the Q&A panel at the bottom of the screen, and we'll work through as many as we can with the time left. Any that remain unanswered, we'll follow up with after the webinar. So for the first question, do you do feature selection inside n-fold cross-validation?
Yeah, I think that question is for me. So the general answer is no, we don't do that. I think what you might do when you do feature selection before anything else is that you bias your data set even before splitting it to the training and test sets. So the answer is no.
Thank you, Mario. Tamsin, I have a question for you next. How much data do I need to build a model with Auto Modeler?
Well, that, as Mario said, that depends. You saw that I was using 130 odd compounds there, but it really does depend on the quality of the data that you have and the type of model that you want to build and the type of property that you're trying to model. So I have seen very useful models, especially categorical models built with fewer data points. And if you've got good, clean data, that can be appropriate. I've seen models built with perhaps as low as 60 in the auto modeler. I know in our Sorella application, we will start to make predictions that use even less data than that. But yes, I think the answer there is it depends.
Thank you, Tamsin. There's another question that's come in, which is, can you discuss more about when it may be appropriate to consider oversampling?
I think that's for Mario.
Yeah, I was just thinking about that. So before you do oversampling, first of all, you have to think about the method you're choosing in order to model your property. So some of the models, as I said earlier, already automatically take that into account, that some of the data points or some of the features of some of the data points are underrepresented, and they automatically give those features more weight. But my suggestion is that if possible, then divide your data into three, as both I and Tamsin spoke before. So 70% for training and 15% for validation, and then train two models. Train one with oversampled data and train the other one without any oversampling, and see which gives you the better result. Because depending on the features and depending on the compounds, oversampling might help, but it also might just do nothing. And now, obviously, if you don't have enough data to do the 70-15-15 split, then based on my experience, if you do oversample, then usually it doesn't make the model considerably worse. So it's worth testing it.
Thank you, Mario. We've had lots of questions, but I'm going to go for one final question. Any other questions we'll follow up with after this session. So the final question is, in preparing your training set, Do you use chemical similarity or experimental data distribution for even sampling? And does the choice of training set preparation have a huge impact on the model building?
I guess this is for me as well. So I'm a huge fan of using random splits. And obviously, I understand that when you don't have a lot of data, then you can't use that. So if we can't do a random split, then what we usually do is Tanimoto clustering. And actually, Tamsin already showed you that we have that in AutoModeler as well. And in certain cases, even the Tanimoto, or based on the Tanimoto similarity, the clustering won't work. So in these cases, we kind of divide the data into, say, two, and then take Y-based sampling, where we just based on the property we try to model, we try to choose an equal percentage of the say active compounds and equal percent of the active compounds, both to the training and the test set. So, and does it have a huge impact? For bigger data sets, I wouldn't say so. For bigger data sets, you pretty much can do any splitting method, and it should work fine. For smaller data sets, yes, it can have a big impact. However, if you do detect that there is a big impact, then I would question if this specific property is modelable at all. Because if your result depends on how you split the data, then one might question, are you just getting lucky with your splits? And if you would do a completely different split, then if your model would be bad, then what would you do?